Today we are going to do the Plonk calculations, just as described in this paper. Plonk permutations over Lagrange basis ecumenical, well, I can't even read this stuff. Ecumenical non-interactive argument of knowledge. I have no idea what these words mean. Anyway, the advantage of the protocol is that it generates a ZK snark using a common reference string. So you still have to have some toxic waste, basically something that is generated, and then you have to forget about a particular value, which is S in this case. But that reference string is not specific to the problem. If you change the problem, if you want to make a ZK snark for something for proving a different statement, as long as the statement is more complex than the original one, you don't have to generate a new reference string. So that's a massive advantage. Okay, so let's go through the actual implementation of the proof. And it starts at page 20 something, 26 I think. 26. Okay, so there we go. On and there. All right, this is here. The problem has to be stated like this. So this is actually the stuff that describes your circuit. In our case, we want to prove the same statement as the one from Vitalik. So Vitalik explained Plonk pretty well, but this time he didn't go through the actual walkthrough of the calculation. And so we are going to do it ourselves. He did describe how the circuit is set up, and we can go over this quickly. So here you will have 1, 2, 3, 4 gates, and each gate is performing one arithmetic operation. So I actually have only 3 gates, because in this particular case, this gate can be combined with this gate. The constant here can be expressed as additional input, because the form is the form of each gate is like this. So you have a multiplication factor for the input A and B, then multiplication weight for the output. So A, B, and C, A are inputs and C is the output. You can express this as, for example, if you want a simple addition gate, you want A plus B equals C, then you will use 1 for KL, 1 for QR, and minus 1 for QO. This one represents the weight of the multiplication. So if you want to do A times B equals C, then you would have minus 1 for QO, QM would be 1, and QL and QR would be 0. And finally, if you want to add a constant, you can have the constant in QC. So actually here, these 2 gates can be combined. We can do QL equal 1, QR equal 1, QC equal minus 1, no, QO equal minus 1, and QC equal 5. And then these 2 gates are. So instead of having all this stuff and do equal 35, I'm going to do minus 30 equals 0. The one advantage of having that as a parameter, and this is also supported in Plonk, is that you can have the circuit have parameter during evaluation, proving, and validation. They call it public input, PI. In our case, PI will be 0, and that 35 will be injected in as QC, for QC equal minus 30. So 35 minus 5, of course. Okay, let's get started. So what we have is F101 is the integers modulo 101. So all the numbers between 0 and 100. Then we build the elliptical curve over this field with the equation y2 equal x cubed plus 3, which leaves us easy generator point, the point at x equal 1 and y equal 2, because 1 cube is plus 3 is equal 4, and which is the square of 2. So that's one generator point. We also need the extension field. So we build extension field as the points of f101 plus the solutions of the equation x squared plus 2. So that's just like you can extend the real field, the field of real numbers, with imaginary numbers to form the complex field by introducing I equal the solution of x squared plus 1. If you find a polynomial that has no solution in your original field, which is f101, you can name that solution an arbitrary name, like we call it big X, and say now that the values in your extension field are combinations of values in your normal field plus the values from your multiplied by your solution. So such as complex numbers are written as a plus bi, where ix squared equals -1. We will write our values in the extension field gf of 101 square as values inside f101 plus values in f101 multiplied by x, where x squared plus 2 equals 0. So it's exactly the same idea here, and we need that to for our pairing function, because the pairing function is not going to take values from E, but from the elliptical curve that is based on this extension field. So exactly the same, but instead of f101 we use k, the extension field. So same parameters. So it's also y squared equal x cubed plus 3. So this defines our elliptical curves. Now the order of g, so how many times you can add g before it wraps around, same way as what's the order of numbers in f101. So the orders of numbers f101 is 101. The order of points in on this elliptical curve over f101 is 17. So we actually can say it's n equals that, and then use that n elsewhere. So we also gonna all the multipliers of points will be modulo f17. So we also introduce the integers between 0 and 16. So f17. In f17, the square roots of 1, so numbers are squares to 1, are 1 and -1, and -1 is 16. So what you can do is 16 is also a square. So we can find the fourth root of 1 by doing it again. So you would have 1 minus 1 and square root of 16, which is 4, so 4 and minus 4. So these numbers, if you raise them to power 4, you will get 1. I store them as a vector because we're going to use them as our evaluation points. So W will be 1, 4, 16, 13. Now the algorithm needs 2, so we're on round 1. No, not yet on round 1. So we are still defining our reference string. Other stuff we need for our reference is labels. So we have 4 X labels for our permutation vector, but we need 12. So we just need to to generate two more sets, two cosets. So cosets are sets that also have are also generated by one value, but they are not obviously not sharing any value in common with the main set. So W is this set. I just have to multiply the starting point by a value that is not in the set, and then we have another set, right? 2, 8, 59, and then a third one multiplying by 3. So I chose K1 2 and K2 3, and I have these like parallel sets. And this was going to be useful because we are still here. We're still calculating these our Q polynomials. And what we do know is that these Q polynomials, they have to interpolate to the values that we expect from A, B, C, Q, L, Q, R, Q, M, Q, O, Q, C at their labels. So for the labels of A, it would be 2, 8, 1, 4, 16, 3. So for example, what we need is that FA of 1 should be 3, FA of 4 should be 9, FA of 16 should be 27, and FA of 13 should be 0. So to calculate this, the coefficients of our polynomial, I need to inverse this matrix. So this is basically solving a linear equation of 4 by 4. You can have this in a little bit more detail if you go to Plonk by, I think the first one. So they explain here a little bit about this part. Is it there? Oh, c'est part 2, I guess. Part 2. Right, so this is the idea. You want to find a polynomial that has 4 coefficients, D, C, B, and A, and you want to match at these 4 different points. So in this case, 1, 4, 16, 13. And you're matching some values that you want. So in that case, it's 3, 4, 5, 9. In our case, it's 3, 9, 27, 0. I'll tell you why it's these numbers. But the idea is that you have this system of equations, which can then be written in matrices. So you have this matrix, the numbers that you want to find, A, B, C, D, and the points that you want to match, the y coordinates that you want to match. So 3, 4, 5, 9. If you want to do that once and for all, you evaluate this inverse matrix. So we do it here. We do this A here. A is this matrix, this one, which is the same as this one. Then we inverse it, and we define. We find the solution to our polynomial, our coefficient, by multiplying this AI, here this is inverse, by the desired coordinates. All right, so we have to do this for A, B, C, Q, L, Q, R, Q, M, Q, and Q, C, and this is done here. So what are these values? 3, 9, 27, 0. For this, we need to go back to this circuit, which is not exactly the right circuit because again we are removing this gate. So this is A. This A is the wire values for A1, A2, A3, and A4. So A4 doesn't exist. We only have 3 gates. The last value here is a dummy gate, so that we have four gates, and it matches the number of W's that we have. So A1 is X, And our solution of our quotient is x equals 3. So a1 is 3. And now a2 is going to be the square of x. So because b1 is also x, and this is multiplication gate. So here we have the output c1 equal x squared, which should be the same as a2. So a2 is 9. And likewise, a3 is the gate is inverse. What I did was to wire c2 to a3, and b3 is x. So imagine these gates are reversed. A3 is gonna be the cube of x, 47. And now we have b1 equal to x, b2 equal to x, and again I reverse this diagram. b3 is x. So 3, 3, 3. And now we have c1, c2, c3 are the outputs of these three gates. So we have c1 is 9, c2 is 9 times 3, 27. And the final gate, the output is 0, because I also have an addition gate. So the last gate is this addition gate, where there's also the minus 30 that cancels out the x cubed plus x. So that's why these are the values of our wires basically. And now QL, QR, QM, QO, and QC represents the actual operation done by the gate. The first one is a pure multiplication gate, so no direct involvement of A1, so that's 0. But we have multiplication, so this 1 for the term A1 times B1. Likewise for the second gate, the third gate combines A3 plus B3, so we have 1 here and 1 here, but no multiplication. And finally, there's for the third gate, there's a minus 30. Then there's no output for the last gate. Everything should balance to 0 already. And for the first gate and the second gate, the output C1 and C2 should be the opposite of the rest. So this is why we have minus 1 and minus 1, because we have basically here A1 times B1 minus C1 equals 0. And here we have A2 times B2 minus C3 equals 0. Okay, so this is our program basically that we wanted to verify, and we encode it as vectors, and then we turn them into polynomials. Right. That gives us these three polynomials, fa, fb, fc, and then these 5 polynomials for the q's. So f, a, b, and c are the solutions, and so we don't want to show this. QL, QR, QM, Q, and QC are public because the verifier also verifies for a given circuit. So he actually has calculated this himself. Okay, so next step is SASBSC, which captures the copy constraints. So far we haven't done we haven't established that A2, for example, should be equal to C1. These equations here represents just the values of the gate, but it doesn't represent the connection between gates. So this is captured here by this permutation vectors. What they say is that SA, so A is labeled by the values 1, 4, 16, 13. B is labeled by 2, 8, 59, and C by 3, 12, 14, 5. So what we say is that if we have an equality, well, for example, we have A2 equals C1, then if you swap these labels, we should have the same result because the values at these labels are the same. So here, the second A2 is this 4, right? So if we don't swap anything, then we would also have the same values for A4, 16, 13, A4, 1, 4, 16, 13. But we are saying that A1 should be the same as B1. So the one that was here was swapped with the value for B1. And the value for B1 is 2, right? 2. B is 2859. So we swap 1 and 2 here. Right? And likewise, we've been swapping all these wires so that whenever there's equality, we swap the indices. And that gives us these indices, 2, 3, 12, 13. So you can verify this is A1 equal B1, A1 equal B1. And this one is A2 equals C1, A2 equals C1, right? And so on and so forth. If you don't need to swap because you don't have any equality, you leave the number where it is. So that also is something that the verifier should know, because that's also part of the problem. So based on this guy, we also calculate the interpolation polynomial, and that gives us SA, SB, and SC. In the paper, they are called sigma 1, sigma 2, and sigma 3. I prefer to call them A, B, C because actually sigma 1 is a permutation for A, sigma 2 is permutation for B, and sigma 3 is permutation for C. But they have put all this permutation in the same set, sigma, so it's really written as a single polynomial in the paper. Okay, so round 1. So now we are finally ready to start the generation of the proof. The first stuff we do is Z. So Z is ZH here. And it's the polynomial that vanishes for every root of unity. So the polynomial that equals 0 at W, W2, W3, and W4. Or W4 is 1. So that simplifies nicely into x4 minus 1 because obviously these are roots of unity, so their powers are raised to the power 4 is equal to 1 by definition. We generate 9 random blending values. So these are whatever you want. So pick 7, 4, 11, 12, 16, 2, so that we hide the actual polynomial A. So polynomial A is this part here. So this is the FA where we calculate, and we add this blending factor, which vanishes at our evaluation points. So ZH is by definition is going to be 0 for every value that we are going to use. So this term doesn't matter, but it makes impossible to figure out. I mean, this original A impossible to figure out from this blended value. So we do the same for B and the same for C. So this is the first round, ABC, and then we evaluate ABC at our our reference point. So the core reference point 1 is the point that we generate during our SRS. So I chose is it here? No, I chose S to be 2. Right, chose S to be 2. And normally you would have to give all the powers of 2 multiplied by G, so that evaluation of a polynomial at S can be seen as a linear combination of the reference string. But I omitted that part because basically we know it's possible to do. So what I did instead is kind of took in the shortcut by saying that we evaluate A, B, and C at the point S, and we multiply by G. So that's what is done here. Obviously, normally you don't know S, so you should not be able to do this calculation directly. But you can still do it by taking the coefficient, for example, 7, 4, 3, 1, 12, 10, and use that as a combination of G, 2G, 4G, 8G, 16G, and 1232G. Okay, so then that gives us the first outputs of the proof, AS, BS, and CS. So these are the 3 first points. Then round 2, is the permutation challenge. Normally, beta and gamma are decided by hashing the transcript, but so that the prover cannot has to commit to a particular value. He cannot choose a suitable value for him. So instead, here to simplify that, I chose a random beta and gamma, so 12 and 13. And then did the calculation based on these values, but any value should work here. So same story here. We are calculating this term. There's a blending thing, but we're doing later. First, we calculate this term here. So this is a product. To calculate the product by doing a loop, this term here is particularly that term here. We start with accumulation at 1, and then we have, okay, so we have Wj. Wj is the same as A evaluated at Wi, and that's because of the way A was formed. Right? A was formed so that whenever you evaluate at these 4 labels, so 1 W, W2, W3, you're gonna get the coefficient. So that guy here is AWI evaluated I. This value here, Wn plus j, is B evaluated at Wi, and this value here, W2n plus j, is going to be C evaluated at Wi. That's by construction of A, B, and C. So we can see that this can be written as AWI plus beta times Wi, right, plus gamma times B at Wi plus beta times K1 times Wi plus gamma times C at Wi plus beta times K2 times Wi plus gamma. So this is our numerator, and we divide by A of Wi plus SA. So sigma is same thing here, right? Sigma of j and sigma of n plus j and sigma of n2n plus j are respectively SA, SB, and SC. So SA at Wi times beta plus gamma plus B at Wi plus SB of Wi times beta. The beta is reversed, but same thing, plus gamma plus C of Wi plus SC times beta plus gamma. So these terms, because the way sigma was calculated by the permutation, lots of terms we cancel out. Anyway, that gives us the 4 values. So values for I equal 1, 2, 3, and 4, right? So that gives us these 4 values. And then we have to interpolate a polynomial that matches these 4 values. So I capture these values here, and then I calculate our term here as the same method. This is the polynomial that interpolates to these coordinates. So that gives us this term, all right? And then we have, we have to blind this same way with 3 values here, B7, B8, B9. So I chose 14, 2, 11. Again, whatever you want. And add our final polynomial. This one here is because there's this term 1 here. We know that it has to go at 1 for x, the first label. Okay, so this gives us our polynomial z of x, and then we evaluate z of x at our secret point s. That gives us this value, and that's the second output, this value here. Okay, round 3 is the quotient challenge. Quotient challenge is going to be super big, but same idea here. We find a value alpha. So alpha is also hash of the transcript. But in our example, we can use whatever we want. So alpha here, pick 15. And we have to compute this polynomial. It's a pretty large one. So you see that ZH is a factor of the polynomial. So what I'm going to do is actually calculate T times ZH and then divide by ZH to get T. All right, so the first term here is going to be T1, and we see it's A times B times QM. So A times B times QM plus A times QL plus B times QR plus C times QO plus PI. But PI is the product input, in this case is 0, and plus QC. So that's the first term. Second term is this one here. A plus beta X plus gamma times B times K1, obviously beta is reverse, beta K1 X plus gamma plus C plus K2 beta X plus gamma multiplied by ZX, the polynomial we have found earlier, right, this guy here. And that's it. That's the, times alpha, times alpha. And that's our second term. The third term, this term and this term are summed together, will cancel out quite a lot. So T3, first we have this ZW, which is going to be used here. So ZW is Z evaluated at X times W. So W is our first root of unity, so that's W1. So now we do minus A plus beta times SA plus gamma times B plus beta times SB plus gamma plus multiplied by C plus beta times SC plus gamma. So it's our term here. And finally, we multiply the whole thing by SZ of WX. So that's this term. And then again multiply by alpha. So that's our third term. And then the fourth term is easy, something that has to vanish at 1. So that's ZX minus 1 multiplied by L, right? And alpha square, right? So that's this term here. This L1 here was not introduced here. This is the Lagrangian that matches, gives 1 at the first coordinate and 0, 0, 0 everywhere else. So that you get 1 for the first coordinate, but nothing for the other ones. So basically, you calculate L by the same technique, where you want to match y equal 1 and then 0 for the rest of the coordinates. So this gives us the four terms of T, and we just sum them together, which gives us T multiplied by Z. So then we divide T TZ by Z. By this time, it should divide properly. So if you have made a mistake, then this polynomial would not be a integer polynomial. We get an error because Z would not divide TZ. Then that gives us T. So T is going to be this guy usually, and T is going to be of a pretty high degree because you're multiplying polynomials together, right? You multiply 3 polynomials of the degree 6. So we split then T in 3 parts. Right? So the split is done here. We collect the coefficients, and we have 3 sets of coefficients, and then we recreate polynomials but of lower degrees out of this coefficient. So at the end, the real polynomial is the sum of T low, T mid, and T high, where you gather 6 coordinates per polynomial. And finally, you evaluate T low, T mid, and T high at point S. So this is down here. And that gives us the third output of the proof. Okay. Round 4 is the evaluation challenge, zeta. So zeta, again, you get a random value. Well, that's not random. It has to be hashed by the transcript so that the prover cannot choose the value he wants. It has to otherwise he can cheat. So normally this value is given by the verifier. But since it's non-interactive, the prover has to pick the value that he cannot predict. Here we set zeta to 5, and we compute this pretty simple stuff, which is the evaluation of A, B, C, SA, T, ZX, and L at zeta, and zeta times omega. W, actually omega. So we have A bar, B bar, C bar, SA bar, SB bar. So sigma 1 is SA and sigma 2 is SB. Then T bar and ZW bar. And I have also L bar, but it's not actually part of this guy. L bar is here. L1 zeta is L bar. And then we have to calculate this R. So R is also, I'm going to break it down to 4 terms. The first term is A bar times B bar times QM plus A bar times QL plus B bar times QR plus C bar times QO plus QC. Right? So that's the first line. Second line is A bar plus beta times zeta plus gamma times B bar plus beta times K1 times zeta plus gamma times Z bar plus beta times K2 times zeta plus gamma, whole thing times ZX, then times alpha. The third one is minus A bar plus beta times SA plus gamma, first term, times B bar plus beta times SB bar plus gamma times beta times ZW bar times SC times alpha. So this is this one. It's kind of not very exciting to see, but hey. The fourth term is ZX times L bar. This is our L bar times alpha square. Right. So now we sum everything together, R1 plus R2 plus R3 plus R4, and that gives us our R polynomial, this R polynomial, which needs to be evaluated at zeta as well. So R of zeta is called R bar, and then the fourth output is A bar, B bar, C bar, SA bar, SB bar, ZW bar, T bar, and R bar. So we have them all now. Yeah, we have the first 4, 7 was here, 4, 5, 7, and then R bar is the 8th one. Now we go to round 5. Round 5 is the open-end challenge. So we also get Vega normally by hashing. This time we choose Vega at 12, and we calculate this guy here. So again, I will calculate first W of zeta multiplied by X minus zeta. So there are 1, 2, 3, 4, 5, 6. There are several terms here. Well, these terms are pretty easy to do, right? You can see that there's some structure. This one will take a little bit more time. So V1 is the low polynomial. Right? So just the low polynomial. V2, this term here, is the zeta 6. Right? We took 6 values. So now to reconstruct the original polynomial, we have to multiply this T mid by zeta power 6. And that's V2. And then same thing for the third term. But this time we have to raise to power 12. So we basically reconstructed the t polynomial and we evaluate it at x, right? So these guys pretty much the same actually, except that we have broken down t into 3 parts, so we have to rebuild it. And now v4 is minus t bar, right? So for the rest, v5, I just do vega times r minus r bar plus vega 2. Is that vega? I don't know if it's vega actually. Well, let's call it vega. A minus a bar, and then vega 3 b minus b bar, vega 4 c minus c bar, vega 5 is sa minus sa bar, and vega 6 is sb minus sb bar. So vega 0 is actually t minus t bar. Right? So we collect all this stuff together into w, which is then v1, v2, v3, v4, v5, sum of all this stuff. But we have to divide by x minus zeta. So if everything was okay, this is also going to be an integer polynomial. So that's our w zeta. Now we have to calculate the opening proof, which is the other polynomial defined like this. So zx minus z bar, or zw bar, sorry, divided by x minus zeta times w. So that's w of zw. So it's also another polynomial. And the final output is these two polynomial, wz and wzw, evaluated at the sequence point. So we do the same thing here. And that's the last term. And the proof collects all these guys together. So a bar, b bar, not a bar, a, b, c evaluated at s. Same for z, t low, t min, and t high. Then wz and wzw evaluated at s, as well as a bar, b bar, c bar, s a bar, sb bar, r bar, and zw bar. Right, so this is the proof. Now for verification. First part of verification is to check that all these points were given, these guys here, they are actually points on the curve. So we didn't do that, but you can check that. It's easy to check by checking that y2 is equal x cubed plus 3. Then you also need to check that a bar, b bar, these values here, are part of this group. And for us, p is 17. So that all these values should be lower than 17. Then the third part is also verifying that the roots of unity 1, 4, blah, blah, are part of this, which is going to be the case here, and didn't check that. And then we have to compute these challenges the same way as the prover has done them. So in our case, they are picked up, so we have to reuse the same values. We also compute this polynomial exactly the same way. The Lagrange polynomial same way. So the only new guy here is epsilon, this u guy. Right. It's a new guy. So also we pick up u randomly. And then we do first this z of z, right? So zeta, we have zeta power 4 minus 1. And so this evaluation of the zh polynomial at point zeta. And the same thing for evaluation at of L1 at zeta. So that's zeta minus 4 power 4 minus 1 divided by 4 zeta minus 1. So these two guys are these two guys here. Pi we can skip because we don't have public input. So we have, this is 0. And then we compute the t bar. T bar is a bar plus this term is 0. So minus a bar plus beta times sa bar plus gamma times bit bar plus beta times sb bar plus gamma times c bar plus gamma times SZW bar times alpha minus L1Z, right, times alpha 2. That's the numerator. And I think that, where's the divider? T bar. And then I divide by Z of zeta, right? So that gives us T bar. Then we do D. Again, D is pretty big, so it's broken down in 3 parts. D1 is A bar times B bar times vega times QM. So this part here is because these are elements of FP of modulo 17. The Sage doesn't like the fact that you're multiplying these numbers by points. So this is basically casting them as regular integers. But you can ignore this part. So that's the first term. Evaluate at S. Plus A bar times vega times QL. Plus plus B bar times vega at QR. Plus C bar times vega at Q times Q, plus vega times QC. Right, so this is the first line. Second line, D2 is similar. A bar plus beta times zeta plus gamma, plus B bar plus beta plus times K1 times zeta plus gamma, plus C bar plus beta plus times K2 times zeta plus gamma, and then evaluate times alpha times vega, then plus L1Z times alpha 2 times vega plus epsilon, and the whole thing multiplied by Z of S. Okay, that's D2. D3 is A bar plus beta times SA plus gamma times B bar plus beta times SB bar plus gamma, multiplied by alpha, multiplied by beta, vega, multiplied by SW bar, and then multiplied by the point SC. Yeah. Okay, so then D is the sum of the three guys, and that gives us this value for D. Then we have to do F. So TLO S plus zeta 6 plus T mid plus zeta 12 times T high. That's the first term. Now we do plus D plus vega 2 AS plus vega 3 BS plus vega 4 CS plus vega 5 SA plus vega 6 SB. It's kind of reversing the stuff we did earlier. Okay, and then that's F. Now we have E. So all these guys are points, by the way. T bar plus vega times R plus vega 2 times A plus vega 3 times B plus vega 4 times C plus vega 5 times SA bar plus vega 6 times SB bar plus epsilon times SW bar. Right, and times G. So that's E bar. Also E bar E. And now finally, we have to do the pairing check. So pairing check is between these 4 points. So the first point here is WZ plus epsilon times WZW. Right, so this is part of the first group. That's why it's indexed by 1. Right, by the way, it's all when it's under 1 is evaluated as S, and then X2 is our S times G2. So same thing, but it's our second group. So the little X here is our S here, and this 2 points are going to be part of the first pairing, and we have 2 other points for the second pairing, which is zeta times WZS plus epsilon times zeta times W, right, multiplied by W of ZW plus F minus E. So that's this term here is this Y1, and the fourth point is simply the generator of the second group. Okay, so if everything goes well, E of x1, x2 should be equal to E of y1, y2. So the pairing check is going to do that. We take these points, we put them in a curve on the second elliptical curve. So this is going to cast this guy to points of E2. And then we do the pairing check. So n is 17, so we can put n here. Of the x1, x2, that's a evaluation of E of x1, x2. And then we do the same with y and y2, right? So if these two values are the same, then verification goes. Oh, everything was good, right? So now we actually can run the whole thing. And so we have the same value. So verification passed. All right, that's super tedious, but that's how you can do. Obviously, computer will do this way faster, but this is how you can implement this circuit in Plonk by hand. Well, not exactly by hand, but step by step. Let's put it this way.